Bismillahirrahmanirrahim. Dear students, Assalamu alaikum. I am here to present you some slides, some part of crystallography portion of the solid state physics. And as you know, this is paper 8 and the course title is solid state physics and I am the instructor. So the crystallography portion constitutes an important part of solid state physics, and almost half of the paper is set from this portion, so that's why you need to be attentive to these slides and presentation. This is just a recap of the slides that have already been taught to you in my previous lectures. As far as the crystallinity is concerned, then materials are divided into these three portions. This is a single crystal for obvious reason, this is a polycrystalline material, and this is an amorphous material. And as far as crystal lattice is concerned, then you know that crystal lattice is actually a portion of the crystal structure, which is the one in here. And if it is combined with its basis, right? So basis is the actual structure of the points or the corners of the crystal lattice, then it constitutes an actual crystal structure, right? So this is the actual crystal structure, and this is the basis, right? And this is the lattice. And as far as the technical description of Bravais lattice is concerned, then this is an infinite and indefinite array of discrete points of any arrangement, right? That is similar with respect to orientation and with respect to the number of neighbors that exists around every point in that pattern. And this is the equation. This is the lattice translational vector represented by R. This is N1 A1. So this A1 is the lattice translational vector along one axis. This is lattice translational vector along the second axis, and the same along the third axis. So a three-dimensional lattice translational vector. This is N1, that is a number of jumps in simple words, and N2 number of jumps, right, in respect of A2, and N3 is again number of jumps in respect of A3. And as I have told you that as far as the Bravais lattice is concerned, then two conditions must be taken into account that should be fulfilled. The first condition is the number of nearest neighbors, and the second condition is the orientation. Like when we consider these 2 points, this is point P, this is point R, then around this point P we can notice 3 number of nearest neighboring points, and around this R point again 3 number of nearest neighboring points could be found. So the first condition is satisfied, number of nearest neighbors, but as far as the second condition is concerned, then the orientation is different, because from this point we see that one neighboring point exists on the right side, one exists obliquely towards this side, and another one is obliquely in the downward direction. So as far as these directions are concerned, then we don't see any neighboring points in these directions, like the one in here. Another direction should be in here, and the third direction should be in here. So that's why this honeycomb in its entirety does not represent a Bravais lattice. And yes, you can say that this Bravais lattice is actually the combination of two sublattices, right? So you should remember this sentence. This honeycomb is actually the combination of two sub-Bravais lattices. And as I stated about the translation of this unit cell, so this is the translation of this unit cell represented by this equation. This is 3a plus 2b for obvious reason. And again, a unit cell. A unit cell is the one right, that fulfills two conditions. And let me again recap these two conditions to you people. The first condition is that two consecutive unit cells should not have any empty space or void, right? Nor they should be overlapped with each other. So these are the two conditions for a unit cell. So once we apply these two conditions on this unit cell, which is E, then yes, these two conditions are fulfilled. Similar conditions are fulfilled by this D unit cell, by this C unit cell, B unit cell, and A unit cell. So we can say that all these are unit cells, right? The coordination number is again a very simple term in crystallography. This is the number of nearest neighboring points in a Bravais lattice, right? And this is a famous number as far as the simple cubic structure is concerned. And this number is 6, and I think this was displayed to you people in the classroom situation. For the body-centered cubic lattice, this number is 8, and for the face-centered cubic structure, this is 12. Whereas the primitive unit cell is actually the one that contains only one point per unit cell. And there is a very simple construction of this unit cell, right? As far as the primitive cell is concerned, then we have like if this is number 1, right, unit cell number 1, then we see that each corner atom is shared by 4 such unit cells. Like this is another unit cell, right, on this side. This is another unit cell on the right hand side, and below we have another unit cell like the one in here. So this point is basically shared by 4 unit cells, and only a quarter part comes to a single unit cell. So in total we have 4 corner points, and so we have only 1 point per unit cell once we add up all these quarter points. Okay, so similar interpretation could be made for this unit cell, which is unit cell number 2, and similar could be made with this unit cell number 3, right? Okay, but as far as this unit cell number 4 is concerned, then we have 2 points per unit cell in here. 2 points per unit cell. This is quite obvious. Why? Because 1 point comes from all these corner points, whereas 1 additional point comes from these 2 midpoints, right? So this is not a primitive unit cell. So the unit cell might be defined with a 1 point enclosed in the center. So like this is a unit cell having only 1 point in the center, right? And this is a primitive unit cell. This is a unit cell, right? This is a unit cell having 1 point in the center, so a primitive unit cell. This is a unit cell, You know why? Because two adjacent unit cells don't have any void, any empty space, and there is no overlapping, so this is a unit cell. So this is a combination of unit cell. Though these types of unit cells are uncommon, we normally don't come across such unit cells, but the display of such unit cells is just to clarify your conception, your concept about unit cells. And again, we can push forward the description, the interpretation of primitive unit cell or primitive lattice cell. This A is a primitive unit cell, B is a primitive unit cell, and hopefully you won't have any confusion, any difficulty in understanding the nature of these cells. So this C, this D, they are unit cells, right? And this G again is a unit cell, right? And again a primitive unit cell. This F is a unit cell. As far as this small a is concerned, a in the lower case, this is not a unit cell at all. You know why? Because by considering such a unit cell, right, adjacent to it, we will observe that there will be either a void, right, an empty space, or an overlapping between the two consecutive unit cells. So this is not a unit cell at all. And this B is a unit cell, yes, but this is not a primitive unit cell. As far as the multi-species are concerned, then how to decide about its primitive nature? Then the thing is only one point per unit cell should come from one type of species, and similar is for another type. Like by considering this unit cell, we have one red point and one green point, so yes, this is a primitive unit cell. But by considering this, we have two red points and two green points, so this is a non-primitive unit cell. And this is a three-dimensional representation of a unit cell, and of course this is a primitive unit cell because we have how many points? 8 corner points, 8 corner points in this unit cell, and each corner point is shared by 8 unit cells, and only 1/8 part comes to a single unit cell. So the total number of points per unit cell comes out to be 1. So this is a primitive unit cell. The volume representation is a very famous formula, which is A dot B cross C. In this case, we have A1, A2, A3 instead of A, B, C. So volume of the cell is A1 dot A2 cross A3 mod in the modulus sign, right? And remember, A dot B cross C is commutative. The order is not imported in here. You can put A3 in here, you can put A1 in here, you can put A2 in here. So it doesn't make any difference. You need to remember this. And how to construct a primitive unit cell in any lattice point, right? This is again very simple. We need to draw lines to connect a lattice point to all nearby points, right? And the second point is that we need to draw normals at the midpoints of these lines, right? And if this is a three-dimensional case, then instead of normals, that would be planes. That's why it's written lines hash planes. And the third point is the smallest volume enclosed in this way is the Wigner sites primitive unit cell. right? So this is a very simple description of how to construct a primitive unit cell in a crystal lattice. And so the area or volume which is obtained in this way is called a Wigner sites primitive unit cell. These are the famous examples of Wigner site cell. You can imagine it for an FCC structure, right? And you can imagine it for a BCC crystal structure, right? So this should look like that. And again, a very important interpretation, excuse me, of 7 basic crystal systems. Okay, as you would remember, I had repeatedly told you in my lectures that we have infinite number of choices to to decide about the lattice translational vectors in any crystal lattice. And these are the lattice translational vectors that form unit cells. Okay, so when we have infinite number of choices to decide crystallographic axes or lattice translational vectors, then the question arises, why do we have only 7 crystal systems? Okay, so the answer is that we always prefer to choose those unit cells that have maximum symmetry and minimum size. Maximum symmetry and minimum size. So keeping in view these two parameters, then we can come up to only 7 basic crystal systems. So out of them, triclinic is the most deformed crystal system, and we don't have any minimum symmetry requirements for that like you see in here, and we don't have any preferable choice of crystallographic axes like the ones you see in here. And as far as the interaxial angles are concerned, we don't have any criteria for that. The next symmetric crystal structure is monoclinic, and for this minimum symmetry requirement is 1-2-fold axis. This is discussed in the class, and the B axis should be the one which is parallel to the 2-fold axis, right? A and C are those axes that are perpendicular to the 2-fold symmetry axis, and alpha and gamma is equal to 90 degree. Orthorhombic is another structure. We have 3 perpendicular 2-fold axes, and we have A, B, and C, and all of them are parallel to 2-fold axes. And as far as the interaxial lengths are concerned, then we have alpha, beta, and gamma. They should be equal to 90 degree, right? And as far as the A, B, and C are concerned, they are not equal to each other. You should know that. And this is the trigonal crystal structure. The trigonal crystal structure is also called a rhombohedral crystal structure, like we see in here. This is a special case of the trigonal system known as the rhombohedral system. This is though not discussed in here, but we have discussed it in the classroom. For this we have one 3-fold axis, and this 3-fold axis is parallel to the C axis, and this C axis is basically the C axis of hexagonal crystal structure. I think, yes, I have shown it to you in the classroom. And the angle requirement is that the beta should be 120 degree, alpha and gamma are 90 degree, A and B are equal to each other. So the tetragonal structure is very simple. So we have one fourfold symmetry axis, and the C axis should be the one which is parallel to this fourfold symmetry axis, and I think this is the one that's the longest axis. And A and B are perpendicular to fourfold, and they are equal to each other as well. And the angles A, alpha, beta, and gamma, they are all equal to 90 degree. A and B are equal in length, as I stated. And this is the hexagonal crystal structure, so you can read all these things in here. And the cubic structure is the most simple and the most symmetric crystal structure. So very beautiful diagrammatic representation for all these crystal systems. But remember, when we include the Bravais lattice type, you know, the Bravais lattice type or the Bravais type is the one once we include centered, cells. So for the triclinic, we don't have any centered cells, any further Bravais lattice type. So we have only one. For the monoclinic crystal structure, we do have a primitive or simple monoclinic and a body-centered monoclinic, like the one in here. Right? This is the symbolic representation for that. And as far as the orthorhombic structure is concerned, we have all the four Bravais lattice types for the orthorhombic crystal structure. P, C, F, I. C is basically this is the representation of base-centered. Okay, this is primitive, base-centered, face-centered, and body-centered. And we have a primitive and body-centered. For the tetragonal crystal structure, we have a primitive, right, and or base-centered for the hexagonal crystal structure. And we have a rhombohedral crystal structure and only one Bravais lattice type, which is simple. And this is basically a spatial representation for the rhombohedral crystal structure. And we have a primitive, a face-centered, and a body-centered crystal structure. Right, so we are entering into a new era, or you can say domain, of crystallography in solid state physics, Miller indices for planes. First, let me tell you very important thing about crystallographic planes. Why they are important in crystallography? Why directions are important in crystallography? To figure out physical properties of materials, various physical properties like electrical properties, mechanical properties, optical properties, and piezoelectric properties, ferroelectric properties. So you can name it. All these properties originate from the crystal structures. And remember, some of the properties may not be the same in one direction than in another direction. Like, I can tell you a very simple example. Like, if light enters in an optical medium which is crystalline in nature and which is single crystal, then the optical property any property. You can name it like the speed of light. The speed of light may not be the same in one direction than in another, right? Or the speed of light along one set of planes may not be the same along another set of plane. So why this is so? Why it happens? What is the physical reason for that? These are important questions that are needed by the crystallographers. So that is why this is very necessary to understand and to investigate crystallographic planes and crystallographic directions. Miller was very famous crystallographer, and he, he succeeded to come up with certain parameters to specify, to index some crystallographic planes. So to calculate Miller indices, we have few steps that need to be discussed in here. Let me just read this text for you. In a Brabant lattice, we often need to describe a plane or a set of planes or a set of directions, or even some individual directions. The Miller indices are a notation for doing this. They are also convenient in X-ray work. So to describe a plane, number first. So now these steps are very important. First, we need to specify a point as our origin. So the point as your origin means you should specify a corner point in any crystal structure. This might be a cubic, this might be any other structure, and the name of the structure is always given in the exam paper. You remember that, right? So if it is orthorhombic, you must draw an orthorhombic structure in the paper. Okay, if it is cubic, you should draw a cubic, and if it is monoclinic or tetragonal or a hexagonal crystal structure, you need to draw that structure. You need to stick to that, right? So you should specify any corner point of that crystal structure, and then find the intercepts of the plane on the three axes defined by the basis vectors. First, you need to define a1, a2, a3, right? Or you may define a, b, c. It's up to you. Or you may define even x, y, z, right? So step number 1 gives 3 numbers. Like you are given a plane, okay? Remember, dear students, you remember, in the paper, you will be either given a crystal structure along with some planes, and you have to find out Miller indices for that plane. So the logic of the questions might be that. Or in another option, you will be given some Miller indices and you have to draw the crystal structure, and you have to show the planes corresponding to the given Miller indices. Okay. So step number 1 gives 3 numbers. We need to take the reciprocal of the 3 numbers, and then we have to divide the reciprocals by their greatest common divisor, okay, which yields a set of integers. So the resulting set of 3 numbers HKL is called the Miller indices for the plane. Okay, so just focus on the symbol. Okay, this is parenthesis, and this parenthesis means that we have only one individual plane, HKL, And if these symbols are enclosed in curly bracket, then that would mean a set of planes, a family of planes. So this is a very beautiful representation of these planes. This is very beautiful. Now you will be in position to understand fully the very essence of crystallographic planes. Okay. Um, but remember, the crystal structure is cubic. The crystal structure is cubic and the planes are different. So this is a model cubic structure. The x-axis is along this, y-axis is towards right, and the z-axis is upward, right? Now first consider this plane, right? Um, as far as the intercepts of this plane are concerned, okay, so we have 1, infinity and infinity, okay, and then we have to take reciprocals of these Miller indices, okay, and they are 1 0 0. And as far as the multiplicity of this 1 0 0 is concerned, then it comes out to be 6. Let me repeat it. I know you may be confused. We consider this plane, right? The light blue plane, and we have considered this corner as the origin, right? So this plane cuts this axis, which is x-axis, in here, 1 unit length distance, right? Whereas this plane is parallel to y-axis, okay, and z-axis. So it means that we have infinite intercepts upon these axes. So that's why we have 1 infinity and infinity, and after taking reciprocals we have 1 0 0, and we don't have any commas in between, and we have to enclose them in parentheses. So this is 1 0 0 because the planes 0 1 0 0 0 1 and then 1 bar 0 0 0 1 bar 0 and 0 0 1 bar, okay, all these planes are equivalent to each other because this is a cubic structure. So that's why we have we can enclose this in the curly bracket, which represents a set of 6 family of planes. So this is called multiplicity of this plane. So hopefully you have got the idea. Let's consider this plane. So again, origin in here, x-axis, y-axis, and z-axis, right? And clearly this plane cuts x-axis and y-axis upon 1 unit length distance, and whereas this plane is parallel to z-axis, that is the plane is having an infinite intercept upon z-axis, okay. So intercepts are 1 1 and infinity. By taking reciprocals of these intercepts, we will have 1 1 0 and enclosed in the parentheses. And as far as the family of planes is concerned, but remember this is for the cubic structure only, okay, the structure is cubic, so we can write it in the curly bracket, the multiplicity comes out to be 6. So you can take any order. You can take any order of these intercepts without bars and with bars. So the total number of planes comes out to be 6. This is another plane, okay, and this plane cuts clearly these three axes upon one unit length distance. So intercepts are 1, 1, 1. The reciprocals are 1, 1, 1 enclosed in the parentheses, and by enclosing them in the curly bracket, the total multiplicity comes out to be 8, right? So you need to figure it out. This is very simple. This is very simple, and owing to the number, we can call it octahedral plane. So this text is very important. You need to read it and understand. The purpose of using reciprocal of intercepts and not intercepts themselves in Miller indices becomes clear. The infinity are removed. Okay, so hopefully you have got that. I think this is sufficient for today. If you have any confusion, any query, just email me or text me. I'm here to clarify all your queries, all your confusions. So in a couple of days you will get my another lecture. So I'm leaving now. Right. Thank you for your attention, and God bless you all.